functions ut bring to the system, so we produce yt, yeah, or us, yeah, there is the transfer function us, we obtain ys, yeah. So in other words, this u, small u, big u, small y, and big y, yeah. The small u represents input, yeah, whereas the small y is the output, and u as the input actually is considered as the forcing functions, whereas y is the response, yeah. So in other words, the small u is also considered as a cause, yeah, and the small y is the effect in this case, yeah. So this is the relationship between input and output, yeah, the input signal going into the systems, and it will be converted into the output, small y, yeah. So in this case, considering that kind of relationships between the input and output, yeah, or the cause and the effect, yeah, we define the transfer functions. There is g, yeah, and here we use a g in bracket s, yeah, which is come out from the Laplace transform, yeah. So gs denotes the transfer functions um, between an input x and an output y in this case. So by definition, the transfer functions gs here, yeah, equal to y ys over us, or the output over the input, yeah, as a function of s. So you have learned about Laplace transform. Ys is equal to L, the Laplace of yt, yeah, and the input u s equal to L u t. So we look into an examples of transfer functions being developed, yeah, from our previous examples on stirred tank heating systems. Yeah. So this is the example that we look into tank with a heater, yeah, and a stirrer here, stir the liquid inside the tank, yeah. So the temperature inlet and the water inlet coming into the tank and being stirred, and it come out from the tank with temperature T and the volume or the amount W, yeah. This one here. So if you recall from the previous dynamic model, assuming constant liquid hold up and flow rates, yeah, the equations 2.36 that we covered last week, yeah, on the numerical modeling, and then we suppose that the process is at a steady state, yeah. So everything here on the left side becomes 0, and on the right side of the equations we have WC times Ti bar minus T bar plus Q bar, yeah. So this is the equation for steady state. And from this one here, go back into this equation 2.26, we will obtain V rho C dt plus WC times all this one here. There is Ti minus Ti bar minus T minus T bar plus Q minus Q bar. Equation 3. Yeah? So equation 2, equation 3. And we also have the equations V times rho C dt um, dash over dt equal to wcti dash minus t dash plus t dash. Yeah? In this case, the deviations variables t dash equal to t minus t bar, and ti dash equal to ti minus ti bar, and q dash equal to t minus t bar. Yeah, and if we take the Laplace transformation of this equation 4 here, this one here, you will obtain E rho C times S T bar T dash S minus T dash 0 equal to WC times Ti dash S minus T dash S minus Q dash S, that is equation 5. And if at the initial steady state, so at steady state that T dash 0 equal to 0, yeah, then we rearrange equations 5, this one here, equation 5 here. To solve for T dash S, we will obtain T dash S equal to K over rho S plus 1 times Q bar q dash s plus 1 over tau s plus 1 times pi dash s equal to 6. Yeah. And here we can say that k equal to 1 over wc and tau equal to v rho w over w. Yeah. So in this case, if you look at these equations here, qs and s here, we can actually obtain the transfer function, which is this one here and this one here, which is the transfer function as p dash s equal to g1 s, the first transfer function, times q dash s equal to plus g2s times pi dash s. Yeah. Where G1 and G2 are transfer functions and independent of the inputs Q dash and Pi dash, then we note that Q1, the process has gain K and the time constant tau, and G2, there is the disturbance, has gain equal to 1 and time constant tau, and the gain equal to G S equal to 0, so which are both first order processes. And if there is no change in the inlet temperature, that is Ti dash equal to 0, then Ti dash S equal to 0. And in this case, we can say that the system can be forced by a change in either Pi or Q. Yeah, let's see in the next example here. Yeah. So what it means is that the conclusions about the transfer functions. Yeah. So we note that the equation 6, this one here, yeah, p dash s equal to k over tau s plus 1 q dash s plus 1 over tau s plus 1 pi dash s. Yeah. This equation shows that the effects of changes in both q and pi are additive. Yeah. And this always occurs for linear dynamic models like the transfer functions because the principle of superpositions is valid. Yeah. So that's the principle of superposition. Yeah. And the transfer functions model enables us to determine the output response to any change in an input. So in this case, we can use the deviation variables to eliminate initial conditions for transfer functions models. Yeah. For example, in that stir tank heater, for example, if we have the value for k equal to 0.05 and the time constant tau equal to 2.0, then t dash equal to 0.05 over 2s plus 1 times q dash with no change in pi dash, and the step change in qt, if you're given that the q 1500 calorie per second to 2000 calorie per second, then q dash equal to the difference 500 over s. So t dash equal to 0.05 over 2s plus 1 times 500 over s, that is equal to 25 over s times 2s plus 1. Yeah. So in this case, uh, what is actually t dash t? Yeah. So from the Laplace transformation, from the Laplace transforms table, from line 13, yeah, table 3.1, which we seen last week, yeah, we have t dash t equal to 25 times 1 minus e minus t over tau, yeah, and ts is equal to 25 over s times 2s plus 1, yeah. So that is um, the transfer functions here. Yeah. So the properties of transfer functions model. First, we look into the steady state gain. Yeah. So the steady state of a transfer function can be used to calculate the steady state change in an output due to a steady state change in the input. So for example, suppose we know two steady states for an input u and an output y. Then we can calculate the steady state gain k from this equation k equal to y2 dash bar minus y1 bar over u2 bar minus u1 bar. Yeah. So this is the steady state gain k for this transfer function. So for steady state gains for transfer functions. Yeah. So for a linear system k is a constant, and but for a non-linear system k will depend on the opening conditions, yeah, u bar and y bar. So the calculations of k from the transfer function model, therefore, if a transfer function model has a steady state gain, then k has a s to the limit of s to 0 of the transfer function gs Yeah. Then this important result is a consequence of the final value theorem. And then with some transfer functions models do not have a steady state gain, for example, the integrating process, yeah, in the next chapter. And then the order of a transfer functions, yeah, if, when we consider a general the n order of the linear ordinary differential equations ODE, then we have an times dny over dtn plus an minus dyn minus 1 dtn minus 1, so on and so forth, yeah, until a0 y equal to dm over dm dtm plus all this one until b0 u as well. Yeah? And taking the Laplace, assuming the initial conditions are all zero, and rearranging give the transfer function as vs equal to y s over us. The standard transfer function vs equal to y s over us equal to the sum of m, the sum of I from 0 to m of VISI over the sum of I from 0 to n AI to SI. Yeah, so this is the transfer function VS in this case. Yeah? So by definitions, the order of the transfer function is defined to be the order of the denominator polynomial, and the order of the transfer function is equal to the order of the ordinary differential equation or the E. Yeah? And the physical reliability for any physical system for n bigger than or equal to m, yeah, in previous equation, um, the equation this one here, 4.38. Otherwise, the system response to a step input will be an impulse, yeah, which is not supposed to happen. Yeah? So, for example, if a not y equal to b1 and u dt plus b not u and step change in u, 4.41. Yeah? And for second order process, for a second order ordinary differential equations of this is the ordinary differential equation, we have d2y over dt squared plus b dy dt plus y equals to u. And the Laplace transform for this one here, table 3.1 for this, we have a d2u d2y over dt squared become a s squared. Yeah? So dy dt become s, so ds, and y become 1. Yeah? Dot ys, yeah, equal to k, what is the output? Equal to k, the constant, and u over us, yeah, the input. So in this case, the transfer function ds given by ys over us equal to k over as squared plus bs plus 1 from this one here. Yeah. So there are from as squared plus bs plus 1, we have two roots. There is the first root s equal to um, b minus b plus minus square root of b squared minus 4a over 2a. Yeah, so this equation that you need to that you use to find the roots of real and imaginary. Yeah? So if we have b squared over 4a bigger than 1, we have real roots, and if b squared over 4a is less than 1, it is considered as imaginary roots. Yeah. So some examples: we have equations 2 over 3s squared plus 4s plus 1. Yeah, the roots of s here, b squared over 4a, here it becomes 16 over 12. Yeah, so um, b actually b is 4, square is 16, and a is actually 3, so 4 times 3 is 12, so become 1.63 bigger than 1, so this is the real, yeah, and no oscillation. But if it is minus less than 1 as given in this second part here, number 2, example number 2, then we have oscillation as given here, yeah, so less than 1 in terms of cos and sine, cos and sine in this case, so yeah, oscillations, either in a cos wave, cosine wave or sine wave. Yeah? And from there, if we apply the Laplace transform in table 3.1 for line 17, in table 3.1, you obtain for e power of minus pt sine t, the Laplace transform will be omega over s plus p square plus the omega square, yeah, and uh, and the roots of s here for s square plus s plus 1 given by this one here, s plus 11 plus square plus root 3 over 2 square. So that is actually the definitions of transfer functions with respect to the output and the input. Yeah. So if you remember your electrical systems, yeah, your lecture on electrical systems, what happened when we have things in parallel and series. So same goes to the control system. Yeah? If you have the control element in with measurements, yeah, the measurements in measurements for your control system either in a series or in parallel. Yeah? So in case of in series, yeah, there have been two consecutive measurements, yeah, in one line in series. Then we related the input and the output u and y will be given as y equal to the transfer function of the first element measurement, the measurement, the first one g1 dot the second measurement g2, the transfer function of second measurement g2. Yeah? So that is called um, instrument or measurement of for control systems in series. And if they are in parallel, yeah, if in parallel, then you apply the additive rule. Yeah? So if in series, it's multiplicative rule. So if in parallel, it will be additive rule. So in this case, in parallel, we will have uh, U1 going into the first measurement G1, we transfer the function G1. Yeah? And then you have another input U2, measurement for the second instrument. You transfer function G2, and then you ending up with the output Y. But because they are in parallel, they become additive. They become additive rule. So yes, the output Y equal to G1 U1 plus G2 U2. Yeah? So I think that is quite straightforward, right? Um, Similar to the electrical system in series and in parallel. So in this case, if you place a sensor temperature downstream from heater tank transport here, in this case, yeah, um, the transport leg of L, this is the time for it to take the measurements from the sensors to the tank. Yeah. With the dead time theta equal to L over V, where V is the fluid velocity. Then in this case, the transfer functions G1 for the tank given by Ts over Us equal to K1 over 1 plus tau 1s, whereas the sensor G2 equal to Ts over Ts equal to K2e minus theta s over 1 plus tau 2s. Yeah? For K2 less or equal to 1, then tau 2 is very small or negligible. Therefore, the overall transfer function Ts over u equal to Ts over t dot t over u. And from the transfer function, it becomes G2 dot G1 and become K1 K2e minus theta s over 1 plus tau 1s. Yeah? So this is the measurement of the temperature and the sensors, the leg, into the leg there, so become in series. Yeah? So this is how it looks like. Now we look into the linearizations of nonlinear models, which is required to derive transfer functions. And here for nonlinear models, when you want to linearize it, you need to have a good approximations near a given operating point. Yeah? So in this case, the gain, the time constants may change with the operating point. And here we can use, in order to linearize it, you can use the first order Taylor series. Yeah? I think you learned it in your maths form, Taylor series. Yeah? So in this case, for dy dt equal to fyu, then fyu approximately equal to fy bar u bar plus the partial differential equation df dy of y minus y bar plus df du u minus u bar. And by subtract the steady state equation from dynamic equations with dy bar over dy dash over dt equal to df dy of y dash plus df du dash. So if you apply that equation to these examples, yeah, where we have the tank now connected to a pump, yeah, with the output of Q naught, yeah. So we control the output Q naught here, and Q1 is the disturbance because of what the amount of water going to the tank, yeah. So this is the disturbance in this case. So in this case, we have ADHDT, where A is the cross-sectional area for this particular inside this tank. Yeah. So A dH over dt. So that will give you the amount of the volume, the area times the height. But in this case, as a function of time, the rate of change in the height dH dt. So equal to Q1, the things are coming in, minus Q naught, the one that going out. Yeah. So this is basically um, we give you Q1 Qi bar equal to Q naught bar at steady state. If you at steady state, this means the height will maintain at steady state. And you will have the area A times dH bar dash over dt equal to Q I dash minus Q naught dash. Yeah, for deviations variables. Yeah. So in this case, we have the area A S times H bar dash S equal to Qi dash S minus Q naught dash S. And suppose that Q naught is constant, then Qi dash equal to 0. And therefore, we have A S H dash S equal to Qi dash S and H dash S over Qi dash S equal to 1 over S. Yeah. In other words, the pure integrator or RAM for step change in Qi. So in this case, we can say that Q naught is manipulated by a flow control valve. Yeah. So for non-linear element, you have Q naught equals QV times square root of H. Yeah, that's given by this graph here, Q naught and level H. And for in this figure 2, yeah, we have a linear model. We have Q dash equal to 1 over RV times H dash. And therefore A dH dash over dt equal to Qi dash minus 1 over RV times H dash. Yeah. And this actually become linear ordinary differential equation in this case. Yeah. So if Q naught equal to CV times square root H, then A dH dt equal to Qi minus CV times square root H. And we apply the Taylor series to linearize the nonlinear model, yeah, performing the Taylor series of right hand side. So we have A dH dt equal to Qi dash minus CV times square root of H bar plus df dqi minus Qi bar plus df dH times H minus H bar. Yeah, so that is for Qi bar. Yeah. So in this case, A dH dash over dt equal to 0 plus 1 times Qi plus Qi bar minus half CV H bar to the power of 0.5 or square root of H and then H bar equal to Qi dash minus half CV H bar to the power of 0.5 minus 0.5 times H dash. Yeah. So in short, we have A dH dash over dt equal to Qi dash minus 1 over R over H dash. And therefore, R equal to 2H bar square root of it 0.5 over CV. This is the example in this case, a schematic diagram of two liquid surge tanks in series. Yeah, the first tank and the second tank. First tank H1, the height of H1, and then the Q1 they go into the second tank, which controlled by H2, controlled by R1, and the output Q2 controlled by the valve R2 in this case. Yeah. So in this case, the input-output model for these two liquid surge tank in series, we have for Qi dash S equal to K1 over tau 1 S plus S plus 1 towards H1 dash S to 1 over K1 times Q dash 1 S towards K2 over tau 2 S plus 1 and H2 dash S to 1 over K2. And then we give you Q2 dash S here. Yeah, the input output model for these two liquid surge tanks in series. Yeah, in series. So finally, this is the procedure for developing transfer functions model from what we have seen this now. So starting from um, Okay. From the dynamic process model of differential equation or dynamic process model, top there is the dynamic process model. We need to obtain the steady state model by setting derivative to 0. And then if the system is linear, then we can subtract the steady state equations and substitute the deviation variables. And if it's non-linear, then we can use the Taylor series expansion to linearize the non-linear terms. Yeah. Once we have linearized it, either direct or through Taylor series, then we can express the model in deviations variable form. Yeah. And from there, you can take the Laplace transform, which the initial conditions are 0. Yeah, and then from there we move to number 5. Algebraically eliminate all outputs except the desired output. Yeah, and from there to number 6. The step number 6, we set all inputs to 0 except the desired input. And step 7, we find the desired transfer function by dividing remaining output by the remaining input, and therefore we get the results. Yeah. If you did not get the results, probably you need to repeat for other inputs. Yeah, or you can also repeat for other outputs as well. And again, hold on again one more time. So this is what you need to know about mathematical modeling. Then from there we obtain the Laplace transform, and then from the Laplace transform we obtain the transfer functions. Yeah. You find it um, difficult to follow.
Yes, very difficult to follow.
Very, very much a lot of maths involved, right?
Yes.
Uh,
Well, that's
so
what
can you give us like
PLC or programmable logic controller are doing. It's not that easy actually, but they have a systematic approach. I can say it's a systematic approach on how to do it, right? So that is actually what
so
we have seen actually step by step on how they obtain from last week we obtain the numerical model for that particular process from our understanding of the fundamental principles of the physics. Yeah. It could be in the form of an energy equation or even different equations. For example, we're talking about momentum, yeah, or just simply a continuity of mass, distribution of mass. Yeah. And then we obtain the Laplace transform, and then here we see how that Laplace transform being used to represent the input and output, and from that output and input we obtain the transfer functions GS. So the GS basically S is in the form of Laplace transform. Yeah, GS equal to YS, the output over the input US. Okay. So from there actually from that transfer function, yeah, which representing the input and the output of each of the element in the control system that can be in series or in parallel. Yeah, so if it's in series, then it will be in multiplicative form, and if it's in parallel, it will be in additive form, yeah, as you can see just now. Yeah, so by doing that actually, um, if we if we um, put that together, you'll find out that it's in the form of matrix. Actually, yeah. So remember the matrix in a MATLAB. Yeah. Remember MATLAB stands for um, matrix lab. Yeah, it becomes MATLAB. Yeah, matrix lab. Yeah. So you have the input related to the output related to the input. Yeah. Y, X. Yeah. So in this case, when you have that kind of system in the form of transfer functions, GS, yeah, representing all the elements in the control system, output and input, yeah, we can program it by using a programming language like MATLAB. I think that one you all understand, right? Yeah, that one you all can appreciate. correct? Maybe you not really appreciate how you develop that um, Laplace from Laplace transform to transfer functions, but from understanding of MATLAB matrix geometry, actually the transfer functions from that Laplace transform into a matrix actually. And you can obtain the output based on the input, which is the combination of many uh, elements in that control system. Any questions?
So,
Yes.
can you make a pre-recorded video on a few examples on the questions?
Um, oh, sure. You want me to repeat? You repeat it?
No, no. Like you make like a question, and you in a video you help to solve the exercise
Oh,
example,
okay, okay. Yeah, okay.
because
We can do that. Actually,
because
if you type if you Google it, right? You just put the Laplace transformation transfer functions. Yeah, it will give you many examples. Yeah, um, where they use transfer functions from Laplace transform to come out with the um, some of the examples in actual process. Yeah? You want me to you want to do it as your assignment if you want?
no.
I think that'll be interesting because it'll be 1 week assignment to refresh your final exam. I think actually I'm tempted to do just that actually. That's why I did not prepare your assignment until today, but I will do it after this week. Yeah, okay. Basically, you need to I give you a process. I describe you an examples, yeah, of a process. It could be similar. Talking about mixing tank, where you have to stir it and come out with the temperature, energy, etc. So you develop the numerical equation. From there, you develop the Laplace transform, and from there you obtain the transfer functions. Um, but of course, before that, you need to come up with the flow diagram of the process first. Agree? I think some of you probably have done it for your pull-out threshold project. Yeah. So before you do anything, before you propose the control system, you need to come out with the flow diagram of the system there, right? So that is integrated systems, but in this class, we learn about numerical modeling, Laplace transform, and transfer functions. We just look at one system. There is the stir tank, right? Whereas pull-out threshold is actually um,
The
a
turbine.
series a series of systems, correct? From uh, the turbine, generate power, yeah, and then to the control systems, yeah. But you need to come out with the flow diagram. Yeah? So if I give you one example, then maybe I can exit from here. This is the last slide anyway. Yeah, I close this one. Okay, you can see this ellipse, right? So if let's say I go to Google here, searching repeat there, transfer, transfer function. So we look into examples of let me see this one first. Can I play this one? too long, but I will cut it short. Can you see this video?
Yes, yes.
Okay. Okay, can you follow that lecture?
Tak ada suara terisi.
Let me start. Okay, just go back to my lecture. So I watched that YouTube on transfer function. Basically, just what I just mentioned to you just now, where you have a process, you need to come up with numerical modeling for it. For just now, they showed a spring, right? For example, and from there they come up with the Laplace transform, and from that Laplace transform, they come up with the transfer functions. Yeah, um, make sense to you? You can follow the lectures now. I can bookmark it and I put it here so that you can have basically you can have it here. Well, yeah,
Thank you, sir.
uh, so YouTube. Here, here. Yeah, so you can repeat the lecture again during your own time, 11 minutes. So 11 minutes worth of lecture. And the questions now, if I give these similar things to you, but I will choose the process, and then you can do it within 1 day or 2 days, yeah, within a 1 week time frame. You think you can do that? This is as your reference, this video as your reference. uh, do you up to the challenge? Are you up to the challenge?
No,
It should be within your capability to do that, right? um,
make it as easy as possible.
yeah, so this is actually with regard to how many together there. Yeah, you can watch this one again and again. This is the flow, basically the flow diagram, and from there they come out with the block diagram. From there they come out with the this is actually a control, closed loop control system. Yeah, ending up there when they come out with the connect to your brain, it's actually part of your control loop system, close closed loop control systems. Yeah. Um, Actually, I'm decided to do that actually, but I haven't decided on which process uh, for your assignment. Yeah, to replace the final exam. Do you think uh, it's a challenge? I did not expect you to come up with the exact questions, but at least you have the basic there, right? Do you think it's okay? I will break the questions into two parts. One part is on this one here, mathematical modeling followed with Laplace transform and the transfer functions, and then the second part will be more on concept-based questions, but still on level 6 on the Bloom taxonomy. Yeah, because when we replace the final exam with assignment, the assignment need to be a complex problem. So by giving you a question similar to this example, it's considered as a complex problem. Yeah? So they cannot think of other simpler complex problem other than this. I think this one is acceptable, and you do have proper guidance to do that in this form, in this video form, on top of the lecture notes. Probably lecture notes is quite difficult for you to follow, but at least you know where you can get the Laplace transform table, for example. Yeah? Understand what the concept of numerical modeling, and finally understand what is transfer functions. as the ratio of the output and the input in the S domain. Okay, are you ready for the challenge? I'm supposed to give my assignment questions to Fikri by 4 o'clock today, so about half an hour. So after this, I will draft one or two paragraph questions. Yeah, I've done the second paragraph. I haven't done the first paragraph, which is this one here. Okay.
Make it as easy as possible. So,
Sorry, you all sound so scared. You can repeat this video again. I already bookmarked it here. Yeah. Yeah, you can go back to Elite and play this video again, and there are of course many other videos also, but this is a good example, yeah? Because they showed you how you use how you develop the numerical model, how you develop the Laplace transform, and finally how you obtain the transfer functions. Yeah? Okay. I mean, I cannot at this moment because they rush me to produce the assignment question. I cannot think of any other simpler, complex problem. So I think this is a simple, complex problem because you will have some guidance to it. Yeah. Of
uh,
course, I will not give you the exact example like this one. It must be different. Then you can justify the complexity of the other things. Yeah?
sir, is there any programs that we need to use?
Problems,
Programs,
programs,
or is it
programs.
handwritten or Word document?
Oh, okay.
Yes.
When you prepare your when you prepare your assignment, I expect you to use words to write your
All right.
report, right?
All right.
But when you describe your work, which software you want to use, most of the time actually in control system, normally we use MATLAB.
All right.
Yeah.
So the assignment, does it require you to use MATLAB?
Um, you only actually you only propose that you want to use MATLAB. Yeah. So when you develop transfer functions, for example, actually you mean you want to use MATLAB. But in this assignment, you are not going to use MATLAB. You only say that you develop these transfer functions and that can be applied to can be simulated using MATLAB. But you're not going to do the MATLAB program.
Ah, all right. Thank you, sir.
um,
Yes,
not that you have to come up in your assignment with a working MATLAB program. No, no. But the understanding that when you manage to develop that transfer function, that means that transfer function can be used in MATLAB program to simulate that control system. So like this one, for example. That's okay.
mm, okay. Okay.
So I'll give you a surprise on 20th of July. You will find your assignment questions. Yeah. So that is the first part of my assignment, which is something like this. But second part will be different. We'll be talking about the overall control system. So the concept of overall control system. So you need to come up with another assignment. So there actually one assignment, but in that assignment there are two parts. One part is on this modeling, and the second part on the concept, yeah, of overall control system on how you um, describe the complexity of a control system, for example. Yeah. So that is the assignment will look like to replace your final exam actually. And Fikri will give you another assignment. So there will be two assignments, one for me and one for Fikri. And in my part, my assignment will be divided into two parts. One part on this one here, mathematical modeling all the way to transfer functions, and the other one is on the overall control system, the the concept, the overall concept of a control system. Yeah? So you need to consider the issue of safety, yeah, and here, and you probably need to do a bit of literature review as well, yeah, to look at some problems that already happened and use that problem or incidents as a basis of your um, explanation in your overall control system, the concept for the overall control system. Yeah. Any questions?
No.
If none, then if you have any questions, you can ask me. But if you don't have, you can leave the meeting. Yeah. I'll be here until 3:30. After that, the last half an hour, I will finalize my examination and I post it to Picture so they can moderate it.